Hello, my name is Telgin Malik. My magic number is ES05927. So for this assignment, I have selected case number three about governance systems and specifically focusing on identity management and voting. Mainly, I choose this topic because identity fraud is a genuine, documented problem in countries across Central Asia and Southeast Asia, especially in my home country, Kazakhstan, where centralized government databases have historically been manipulated and sometimes even breached. Blockchain-based identity system addressed directly as blockchain is being considered for its domain because its core properties like immutability, decentralization, and cryptographic security map directly onto the problems of data tampering and lack of public verifiability that plague traditional government record systems. So throughout this presentation, I'll be discussing a non-cryptocurrency application, as the focus is entirely on using blockchain as a trust infrastructure for public governance. Now, moving on to the next slide, it shows the block data structure specific to a government identity and the voting blockchain. And as you may see, each block has three layers. First, the block header. This contains the block's own hash. The previous block's hash, which is what chains blocks together and makes tampering detectable. A UTC timestamp, numerical root, that is a single cryptographic summary of all transactions in the block. Validator signatures from the consensus nodes, and the block number. Then the second, the transaction data layer. This is specific to our use case as we store the citizen's ID as a hash, not as raw data, which protects privacy while still allowing verification. And there is a digital signature from the citizen's private key, proving the transaction is authentic. The transaction type field records what happened, whether it is an ID being issued, a vote being cast, or a record being updated. And also we store a reference to an IPFS hash for any supporting documents to watch to store on chain. A status flag indicating whether a record is valid or revoked, and the identifier of the issuing government authority. Third, the last one, the smart contract reference layer that stores the contract address and event log hash for audit trail purposes. And every single field serves a specific purpose related to integrity, privacy, or auditability in this government context. And now let's compare how the same identity data would be handled in a traditional centralized system versus a blockchain. So, as you know, in a traditional database, a single authorized party, like the government minister or database administrator, is the one who controls the data entirely. They can alter, delete, or selectively share records. And this is not hypothetical, as there have been many documented cases where electoral rolls and identity records in various countries have been manipulated by insiders. And of course, the data integrity relies on the honesty of whoever holds the keys. But blockchain fundamentally changes this, as once data is written to the chain, it cannot be altered without invalidating every subsequent block, and this is detectable by every node in the network. Additionally, access control is distributed, as there is no single government department or official who can unilaterally change a record. Also, transparency is built in a public permission model. Any citizen can verify the state of the ledger, while only authorized nodes can write to it. And the tamper resistance is cryptographic rather than procedural, meaning it does not depend on trusting an individual. And additionally, auditability is automatic and continuous rather than periodic and paper-based. And in summary, this is why blockchain is a more suitable choice for the domain. Basically, it transforms trust from something you have to assume into something that is mathematically guaranteed. And now moving on to the next slide. The primary threat that I want to address is the data tampering by insiders, the corrupt officials or malicious actors who have legitimate access to a centralized government database. And without blockchain, this is remarkably easy to do and very hard to detect, as the database administrator can alter voter roles, revoke a legitimate identity card, or maybe add fraudulent entries. And unless there is a separate independent audit system, which often does not exist, or maybe is itself controlled by the same authority, there is no reliable way to prove that tampering occurred. And this is exactly the vulnerability documented in the cyber procurement context by Filmo Satyen, where paper-based scoring and offline decision and records were routinely manipulated. And in an identity or voting system, the consequences are even more severe as you can disenfranchise citizens or even steal elections. So, blockchain causes vulnerability through three mechanisms. First, of course, every record includes a cryptographic signature from the citizen and the issuing government node. Basically, you cannot forge a record without processing the private key of the legitimate party. Second, every block includes the hash of the previous block, and of course, altering any record changes its block's hash, which cascades forward and is immediately visible to every validator node in the network. And third, smart contracts reinforce the rules of the system automatically. Who can issue an identity, who can update it, and what conditions must be met without requiring any human intermediary to mediate the transaction. And also, the Ateneo Research Group's prototype confirmed that this works in practice, as their system ensured unauthorized accounts could not change the ledger state. And now, moving on to the next slide, slide number 5, why proof of work is unsuitable for a government identity system. As I found, it is for three reasons. First, it consumes enormous energy. Second, its transaction speed is far too slow for a national scale identity verification or voting. And third, it is permissionless. Anyone can become a validator, which is of course inappropriate when validators should be legally accountable institutions. But in my proposed alternative, which is delegated proof of stake, or in short, DPoS, validators are elected or appointed to government institutions like an election commission or Ministry of Interior, who are known and auditable and can be removed if they misbehave. Also, energy use is negligible. Throughput can reach tens of thousands of transactions per second, and accountability is built in. Also, it is important to mention that Alexopoulos confirms that permission blockchain with a count of validators is consistently the preferred architecture across the real European e-government implementations. These are my five academic references, all from peer-reviewed journals or conference proceedings. They cover blockchain governance procurement, open governance transparency frameworks, a working prototype of a governance blockchain system in the Philippines, a systematic review of blockchain for information sharing, and a European landscape analysis of blockchain in e-government. So, thank you for watching.